Welcome to tutorial number 11 of the Standard Amateur Radio course brought to you by the Radio and Electronics School. In this tutorial we're going to be talking about resonance. We're not going to be talking about antenna resonance at this stage. We're going to just talk about the resonance of inductive and capacitive circuits. There's not a lot of questions in the standard exam about LC circuits, and we'll try and be concise and just keep it to what you need to know for the standard assessment. We'll be giving you some background on resonance that you won't be assessed on, but this background will make the whole concept of resonance a little easier for you to understand. We've learned a lot about capacitance and inductance and capacitive reactance and inductive reactance. We've learned that an inductor can store energy in its magnetic field. And a capacitor can store energy in its electric field. Sorry about the rough writing, but I'm sure you can read it. So a capacitor can store energy in its electric field, and inductance can store energy in its magnetic field. All the fun begins to happen when we put these two components, L and C, together. We can put them together in series, or we can put them together in parallel, and the effect is exactly the same, and that's what we're going to be talking about in this tutorial. We've also learned that inductance has a property called inductive reactance, measured in ohms, and that is equal to XL equals 2 pi FL. We've also learned that capacitance has capacitive reactance in ohms, and that is equal to XC equals 1 on 2 pi FC. XL, XC and R are all types of opposition to current flow. The difference between them is that R is the only electrical property that dissipates heat. Inductive and capacitive reactance can restrict the amount of current flowing in the circuit, but it does this without producing any heat, as does resistance. The combined effects of all the oppositions, resistance, inductive reactance and capacitive reactance, the combined effect of all of those together in a circuit is what we call impedance, and impedance is measured in ohms. Suppose we were to give this circuit some energy. Suppose we were to charge the capacitor, remove the capacitor from this circuit, take it out and charge it up to the battery voltage, whatever that might be, and then connect it back to this circuit. What would happen? Well, the minute you connected a charged capacitor back to this circuit, the capacitor would begin to discharge through the inductor. Now I'll presume that the top is positive and the bottom is negative of the charged capacitor. So when we put the capacitor back onto the inductor, the capacitor will begin to discharge through the inductor in this direction. As the current discharges through the capacitor, there will be a magnetic field created around the inductor. They are magnetic lines of force that I'm drawing. So as the capacitor begins to discharge through the inductor, a magnetic field is created around the inductor. That means that the energy in the electric field of the capacitor is being transferred to the magnetic field of the inductor. What will happen when the capacitor has discharged fully into the inductor? Well, the magnetic field around the inductor is supported by the current flowing through the inductor. So once the capacitor has discharged through the inductor, the magnetic field around the inductor will collapse. When the magnetic field around the inductor collapses, there will be relative motion between a magnetic field and the inductor, and a voltage will be induced into the inductor, and that will cause a current to flow in the opposite direction, which will charge the capacitor. So what we're saying is that if we charge the capacitor, we store energy in its electric field. If we then connect the capacitor to an inductor in either series or parallel, that has to be something in the series circuit to complete the circuit. But let's talk about the parallel circuit. We charge the capacitor, we store energy in its electric field. The capacitor will now discharge. If we connect it to the inductor, the capacitor will discharge through the inductor, creating a magnetic field about the inductor. When the capacitor is fully discharged, the magnetic field around the inductor will collapse. That will induce a voltage by Faraday's law into the inductor, creating a voltage across the inductor, and the inductor will now charge the capacitor. When the magnetic field is totally collapsed, the capacitor is fully charged, or it's going to get as much charge as the inductor had to give it. And now the capacitor will again discharge through the inductor. So we're going to get an alternating voltage here. We're going to get a sine wave of voltage, and that's happening because there is an exchange of energy between the electric field of the capacitor and the magnetic field of the inductor. The capacitor gives its magnetic energy of its electric field to the inductor, and when that's done, the inductor gives its energy of its magnetic field back to the capacitor. And so we have an oscillation, we have a toing and froing of energy from the inductor into the capacitor. We have an oscillatory current flowing here, and that will produce a sine wave. And what we need to know is what the voltage of that sine wave, what the frequency of that sine wave will be. If we don't have to charge the capacitor. We could just, for example, build this circuit and then push a bar magnet past the inductor. That will start the ball rolling, because putting a bar magnet past the inductor would induce a voltage into the inductor. That voltage would charge the capacitor. When the capacitor was fully charged, then there was no magnetic field. The capacitor would discharge through the inductor, giving the inductor a magnetic field. When the capacitor is fully discharged, that magnetic field collapses, induces a voltage into the inductor, which recharges the capacitor, and that produces a sine wave of energy. If we don't keep giving the circuit a little kick, because even though there's no resistance in this circuit, there is resistance really in the inductance wiring, and there is resistance in the plates. So if we were to give this circuit a little bit of energy, it would produce a sine wave at a certain frequency, and that's what we're going to look at shortly. And the sine wave wouldn't continue forever. It would be called a damped sine wave. Just give me a second. If it were a perfect circuit without any resistance, it would keep oscillating forever. But because it has resistance, the frequency stays the same, but the amplitude of the oscillation decreases until it eventually stops. And that's called a damped oscillation. So the frequency stays the same, but the amplitude decreases because of the resistive losses in this circuit. A circuit that can sustain, an LC circuit that can sustain an oscillation for a long time, means that it's got very few losses. Such a circuit is said to have a high Q. That's a capital letter Q. And Q represents the losses of this circuit. If the Q is high, the quality is high, that means this circuit has very few losses, and this oscillation will continue for much longer before it totally peters out and is damped. So high Q means high quality, low loss circuit. Low Q means a very lossy circuit. If this circuit was very, very low Q, we might only get a couple of sine waves before it stops. So that would be very low Q, and this would be a much higher Q. It really just indicates the losses of this circuit. A high Q circuit would sustain an oscillation for a long time, a low Q circuit would not. I think you'll have any problem seeing how this circuit will oscillate and exchange energy between the capacitor and the inductor. The toing and froing, the resonance in electronics in an LC circuit is the exchange of energy between the capacitor, the electric field of the capacitor, and the magnetic field of the inductor. What we need to see is how this circuit behaves, and we also need to try and work out at what frequency they will oscillate. So we know the value, we know what L is, we know what C is. We should be able to work out a mathematical equation for how quickly this circuit oscillates. In other words, we should be able to work out easily the frequency of the oscillation of any C and any L. We learned in the two previous tutorials that the reactance of a capacitor in ohms, XC equals 1 over 2 pi FC. We also learned that the capacitive reactance in the inductive reactance in ohms, XL, equals 2 pi FL. What we're going to do here is draw a graph of frequency versus inductive reactance first. Because XL equals 2 pi FL, and that's a direct proportion, what that means is that if F or L increase, XL will increase. If F or L decrease, XL will decrease. That's a direct proportion. So if we were to make a graph of frequency versus inductive reactance, we would get a straight line, something like this. I'll just make that line a little bigger, and I'll give it some color. There we are. Can you see what's happening here? It's simply a graph of frequency versus inductive reactance, and as frequency increases, inductive reactance is increasing because inductive reactance is directly proportional to frequency. And we're leaving L the same, so we're just changing frequency, and that's changing the inductive reactance, and we get a graph like that. We get a linear graph. What if we were to draw a graph of capacitive reactance versus frequency? Well, when the frequency is very low, and the frequency is very low here because frequency is increasing towards the right, when the frequency is very low, this is very small, capacitive reactance is very large. So whereas inductive reactance starts out from zero, capacitive reactance at a low frequency is already a very high value. So if we were to draw a graph of capacitive reactance versus frequency, we would have to start off on the top up here, and as the frequency goes up, the capacitive reactance would come down like that. I'll just make that line size a bit thicker. And there's our graph of capacitive reactance versus frequency. As the frequency increases, the capacitive reactance decreases. As the frequency increases, inductive reactance, the blue line, increases. The interesting thing is there is a frequency where the inductive and capacitive reactances are exactly the same. And I'll mark that on the graph for you. This is the frequency here where the inductive and capacitive reactances are the same. I'm a little bit off. little bit off. See if I can move that over a little bit. There we are. So at this frequency, whatever it may be, the inductive and capacitive reactances are exactly the same. It's that frequency that this capacitor and this inductor creating this inductive and capacitive reactance, it's this frequency here that that LC circuit would be resonant. The resonant frequency then, or resonance, occurs when XL equals XC. And since XL equals 2 pi FL and XC equals 2 pi FC, 1 over 2 pi FC, we can say that at resonance 2 pi FL equals 1 over 2 pi FC. Forgive my lazy use of the pi there. It's a little bit hard for me to type a pi symbol in its application. So resonance occurs, the resonant frequency occurs when the reactances are equal, when 2 pi FL equals 1 over 2 pi FC. Now if you transpose that equation for F, and it's not hard to do, I'm not going to do it for you. I'd be happy to, but you just don't need me to do it. If you transpose 2 pi FL equals 1 over 2 pi FC for F, you get FR equals 1 over 2 pi root LC. And that's probably the most important equation in radio, because what that equation is telling us is the resonant frequency of an inductor and capacitor pair. So we don't have to draw a graph and set up equipment and plot the inductive reactance and plot the capacitor reactance to work out the frequency. Simply by a transposition of that equation, we get this equation, which is the equation for resonant frequency, FR equals 1 over 2 pi root LC. So if we know C and we know L, we can work out the frequency at which they will resonate or exchange energy and produce a sine wave between their electric and magnetic fields. I'll just remind you of another thing. The total opposition to current flow in an AC circuit is the combination of all the oppositions. Impedance is the combined opposition of resistance, inductive reactance, and capacitive reactance. And when all those oppositions are working together, we call it impedance, and it's measured in ohms. You can't just add them up, there's equations for it, but that's what impedance means, the total opposition to current flow in an AC circuit. And we've also learned that to determine the resonant frequency of any inductor or capacitor, we simply use this equation, FR equals 1 over 2 pi root LC. Notice how L and C are in the denominator. So because they're in the denominator, that's an inverse proportion. So if you were to make L and C very large, they would resonate at a very low frequency. If you were to make L and C very small, they would resonate at a much higher frequency. You need to understand how FR changes when L and C is changed. And all you need to remember is that if whatever L and C do, F does the opposite. So if they're getting really, really big, F is getting really, really small. If L and C are getting really, really small, then FR is getting really, really big. This circuit is a series circuit, a series LC circuit, because L and C are in series. This circuit is a parallel LC circuit because L and C are in parallel. Now, if we were to draw a graph, let's start with the parallel one. If we were to draw a graph of impedance, which is the total opposition to current flow, versus frequency of a resonant circuit, we would get different graphs for both the series and parallel circuits, and you need to know this because the impedance of a parallel circuit is maximum at resonance, and this red line here indicates the resonant frequency of each of these circuits. So that red line there is the resonant frequency of the series circuit. This red line here is the frequency of the parallel circuit. On the horizontal axis, we've got frequency increasing to the right and impedance increasing upwards. So if we were to draw a graph of impedance versus frequency of a parallel tuned circuit, we'd find it reaches maximum impedance at the resonant frequency, and the graph would look something like this. Peaks at very high impedance at the resonant frequency, and going past the resonant frequency it drops off again. So with a parallel circuit you have maximum impedance at resonance. So as you approach the resonant frequency, the impedance increases. When you hit the resonant frequency, the impedance is maximum. When you go past the resonant frequency, the impedance drops off again. This circuit is very, very handy because it's frequency selective. It behaves differently at different frequencies. So we can use LC circuits, for example, to select radio waves or to build filters with. The LC series circuit is a little bit different. At resonance, an LC series circuit has minimum impedance. So at resonance, the impedance is going to be minimum. So the graph of impedance versus frequency for a series LC circuit is something like this. So an LC circuit has minimum impedance at resonance. A series LC circuit has minimum impedance at resonance. A parallel LC circuit has maximum impedance at resonance. So we've learned then that a series LC circuit has minimum impedance at resonance and a parallel LC circuit has maximum impedance at resonance. What I'd like to show you now is, we talked earlier about Q. Q is the quality of the circuit, and what I'd like to show you is how the Q of these circuits would affect their impedance versus frequency curve. What if I was first to draw a high Q curve for a parallel LC circuit? Well, a parallel LC circuit reaches maximum impedance at resonance. So let's draw a very high Q parallel LC circuit. It would be something like this. So that would be high Q. So this circuit is very frequency selective. And it could be used to select radio stations, or it could be used to filter radio frequencies. What if I had a lower Q circuit? I'm just going to change my pen color so it'll look a bit clearer for you. Let's draw a low Q parallel LC, a lower Q parallel LC circuit. Doesn't quite peak at the same high impedance. So that would be a low Q or lower Q. And if we had an even lower Q than the green line, it would go like this. So it starts to flatten out. So that's very low Q. We want our circuits to be high Q because we want them to be very frequency selective, and the pink graph of impedance versus frequency shows how frequency selective a very high Q circuit is. If we were to draw the same graphs for a series LC circuit, well, let's draw a high Q one first. So that's high Q. And I think you can work out what's going to happen now. It's simply going to, with a lower Q circuit, it's simply going to flatten out. So that's lower Q, low Q, and this is very low Q. low Q circuits, if we made any of these circuits begin to oscillate and they're a low Q, we would get a very, very quick damping of the oscillation, and it would peter out very quickly. If we used one that was a very high Q, then the amplitude of the oscillation would be sustained much longer because there's less resistive losses in the circuit. Well, that may not sound like a lot of theory for LC resonant circuits. However, that's about all we need to cover for the standard assessment. So what I'm going to do now is take you through some trial questions of the type that you could expect in the exam. And there aren't, it's not a big section. You're not going to get specifically a lot of questions to do with LC circuits. You may get one. You will get more questions about resonance to do with antennas, and we'll be discussing antennas later on in the course. Okay, let's have a look at question 8.1, and it's asking us to identify the formula for resonance, and we've got 4 formulas to choose from, and you don't need to remember this formula for examination purposes, but I believe you need to remember it for exam passing purposes. It will be on your formula sheet, but I think it'd be a good idea if you just remember FR equals 1 over 2 pi root LC, and make sure you know how FR changes when L and C is changed. So the correct answer for question 8.1 is A, of course. FR, resonant frequency, equals 1 over 2 pi root LC. Question 8.2. The essential components of a tuned circuit are a capacitor and an inductor. Remember, a series LC circuit has minimum impedance at resonance, and a parallel LC circuit has maximum impedance at resonance. Question 8.3, decreasing the amount of capacitance in a tuned circuit. So we're being asked here to apply the equation FR equals 1 over 2 pi root LC, and C in the equation is getting smaller. And remember that F is inversely proportional to F and C, or the square root of F and C. So decreasing the amount of capacitance or decreasing the amount of inductance in a tuned circuit will raise the resonant frequency. Question 8.4. At resonance, the impedance of a parallel tuned circuit. You've got to be careful here not to mix up parallel and series. This is a parallel tuned circuit, and a parallel tuned circuit at resonance has maximum impedance, or impedance at a maximum value. Question 8.5. At resonance, the impedance of a series tuned circuit. Now, what you have to do, just to remind you again, you really have to look at whether they're talking about a series or parallel tuned circuit. A series tuned circuit at resonance has an impedance that is a minimum value. Impedance is the total opposition to current flow in an AC circuit. It's the combined oppositions of resistance, inductive and capacitive reactance. Question 8.6. The Q of a tuned circuit is a measure of, well, it's a measure of how the quality of the circuit, and it's a measure of the losses of a circuit. So the lower the Q, the greater the losses of the circuit, and the higher the Q, the less the losses of the circuit. So the answer is B. Well, that's it for tutorial number 11. You can test yourself on drill number 8, tuned circuits. As I said before, there's not an awful lot on series and parallel tuned circuits in the standard about resonance, but there is a lot on resonance to do with antennas, which we'll be covering later on. Hope you enjoyed this tutorial. Thank you for your work. I hope you're enjoying the course. This is Ron, VK2DQ. I'll see you on the next tutorial. Cheers for now.